Hey everyone, so today we are talking about our second out of three trends, and this has to deal with ionization energy. So let's go ahead down here and let's start talking about ionization energy. And you might be saying, what is ionization energy? Well, if you think about an ion is an atom with a charge. Ionization energy is just the energy it takes to knock out an electron. Okay, so it's just the energy it takes to make an atom an ion in terms of knocking out an electron. Okay, in order to get rid of those electrons, you have to put a certain amount of energy in there in order to knock that electron out. So that's what we're going to be talking about today. It's got a little bit extra. It's not as long as atomic radius, but we will get through it. So ionization energy, if we draw another outline of our periodic table, ionization energy increases as we go up and as we go right. So it increases as we go right and increases as we go up. This is once again this is the opposite. I shouldn't say once again. This is the opposite of atomic radius. We increase as we go up and increase as we go to the right. So let's explain the easiest ionization energy trend, which is going right. Why is it like that? So let's look at something like sodium, which will have a low ionization energy, and then argon, which has a high ionization energy. So let's go ahead and let's draw sodium. It's got 11 protons in the center. It's got 2 electrons, then 8 electrons, and then it's got that 1 valence electron. So it's going to have a third energy level and 1 valence electron. Argon is going to have 18 protons. It's going to have 8 electrons, and then it's going to have 8 more electrons. Its third energy level. Okay, so here's something about atoms that we haven't talked about. Atoms always want their outer shell filled. Okay, they want it full, which just happens to be 8 electrons. Okay, so all want 8. It's called the octet rule. They all want 8 in their outer shell, unless they are down these little ones, then they only want 2, since the inner shell only holds 2 electrons total. So right now, argon is really, really happy. It does not want to get rid of an electron. It's already got a filled outer shell with 8, so it would take a ton of energy. I'm going to draw it as a nice high frequency wave to knock out an electron. Okay, argon doesn't want to give up an electron. It would take a ton of energy and knock it out, a huge ionization energy. But if I look at sodium, okay, sodium only has 1 electron here. It's kind of like, you know what? I want to get rid of this guy, because if I get rid of this guy, then I have a whole filled outer shell right underneath here that will make me happy. So this sodium only takes a little bit of energy in order to ionize it. So its ionization energy is really low. That energy will come in, it'll knock out that electron, and then sodium will have a +1 charge, but it'll be a lot happier because now it has that filled outer shell. So ionization energy increases as we go right, because we have because argon has is already filled, so it does not want to get rid of an electron. Okay, so it takes a lot of energy to get rid of it. Sodium, it's really small because it had that 1 valence electron. He's ready to give it away as soon as possible so it could have its filled outer shell. Okay, same thing kind of with fluorine, right? If we were to look at fluorine, and I'm going to erase sodium here so I could draw fluorine. Fluorine, it's got 9 protons. It ends up with 2 underneath. And let's look at, it's got 7 electrons in its outer shell. It's not going to want to give up an electron either. It's going to want an electron, so it's going to attract electrons. So if you try to get rid of an electron, it's going to take a ton of energy as well. Not as much as if it had 8 already, but a lot, okay? Because it'd rather just attract an electron into its outer shell than get rid of 7 other electrons, okay? So ionization increases as we go right because elements want 8 electrons. When you get farther right, they get closer to 8, so it takes a lot more energy to get rid of those electrons, okay? With helium, it wants 2, right? And it's already got its inner shell filled with 2, so it doesn't want to get rid of them as well. Let's talk about the trend, why it increases as we go, as we go up. So let's look at an example of, let's just do neon and argon. So neon's got 10 protons, which it'll have 2 inner electrons, then 8 outer electrons, and then argon will have 18 protons. And then it has that third energy level, okay? So if I asked you which one is going to be harder to knock electrons out of, it's going to be neon, okay? It's going to be neon. It's going to be really hard to knock an outer electron out of neon than it is argon. Why is that? The reason being, okay, the thing that attracts protons and electrons together isn't just how much there is of each one, but it's also their distance. These protons are really close to these outer electrons, so they got a nice, strong grip on one another. This outer electron in argon is a little bit farther, so the energy is strong, but it's not as strong as it is with neon, okay? So the reason why neon has a stronger ionization energy is because the electrons are a lot closer to the protons. There's also this thing called electron shielding. Okay, electron shielding. So what happens is these protons have a really strong pull on their inner electrons. Then as you go farther and farther out, these electrons start to get in the way of one another. So let's go down to the bottom and let me draw this. Let's draw krypton, which has 36. Okay, krypton has 36 protons. Okay, right at the beginning, those 2 electrons right at the start are going to be pulled in really, really close because they're right next to that nucleus, and there's nothing in the way from stopping that force of protons. As we go to the second energy level, okay, those electrons are pretty close too. There's not really a whole lot in the way. The protons are able to grab onto those electrons without interference. But as we get farther and farther out, okay, those electrons start to get a little farther out and don't have as strong as a pull because the other electrons start getting in the way, right? If you're sending out an attraction force this way, that electron kind of shields the force and blocks this other electron from getting the pull of the protons. And that happens as we go farther and farther out. The more electrons you go out, the more likely they're able to get in the way and block those other electrons from being attracted to the nucleus. Okay? So what happens is that it's called electron shielding. Their electrons are closer together. They're able to be pulled closer to the center. Argon electron shielding prevents there from being such a stronger pull on those outer electrons. So if I ask you, why does neon have a higher ionization energy than argon? It's that argon has more electron shielding. The pull from those protons is blocked or shielded from those inner electrons, so those outer electrons aren't as attracted to the nucleus. Okay, so those are our trends. When we go this way, it increases because they get closer to a filled outer layer, so they don't want to give up electrons. As we go up this way, it's because the lower atomic level electrons have less electron shielding. These ones down here have more electron shielding, so those inner protons can't pull on those outer electrons as much. last thing that you're going to be dealing with is a little ionization energy numbers, and you're going to identify what type of element I'm talking about. Now, this is tricky at first, but if you give it a little time and think about it, it is not that bad. And I made a mistake by thinking I can erase all this in a quick amount of time, so I'm sorry about that. But what I'm going to do is I'm going to give you a list of ionization energies. That'll be ionization energy 1, ionization energy 2, ionization energy 3, 4, and so on and so forth. And then there'll be a list of numbers. So this might be 232. This might be 450. This might be 1535. 2224, and then 2784. Okay, and what I'll do is I'll say this element is in period 2. Which element is it? Okay, so I got an element that's in period 2. Remember, period 2 means just row 2. Okay, so this element is going to be in period 2 or row 2, which is going to be up here. Sorry for moving away from it. So it's going to be either lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, so what is happening here? We got to use these energies to help us figure it out. And what these energies are is the energy it took to knock out an electron. And what you're doing is you're looking for the biggest increase in ionization energy, okay? So from ionization energy 1 to 2, there's not really that big of an increase. It's like 218 ionization energies. These are kilojoules, okay? So that's not a big increase. From ionization energy 2, that's a pretty big increase, right? That's about 1100. Okay, that's a big increase. Here, not really that big of an increase, 700. Here, not really that big of an increase, 500. So the biggest increase we have is from ionization energy 2 to ionization energy 3. What does that mean? That means that we have 2 valence electrons. Okay, and I'll explain here in a second. So say we got an atom with a nucleus, it's got an inner energy shell, it's got 8 energy shell, and then let's say it's got 2 valence electrons, like I said. Okay, so if that first ionization energy is small, that means that the first electron was really easy to knock out. Okay, so this first electron was really easy to knock out. That first ionization energy took it out no problem. This ionization energy, it was a nice little jump, okay, not a huge one, but just a little jump. So that second ionization energy was really easy to knock out, okay? But now that we've knocked out those 2 electrons, now we have a nice outer filled shell. So what would you expect the ionization energy to do? Increase a bunch. So that means that it takes a lot more energy now to knock out this next electron because this atom is happy. Okay, it's got its filled outer shell. So what you have to do is you have to look at these, you have to see where the jump is, and that tells you that this had 2 valence electrons. Okay, so we know it's in period 2, it has 2 valence electrons. Well, if we go back up, period 2 is row 2, and remember these guys have 1 valence electron, 2 valence electron, 3, 4, 5, 6, 7, 8. So period 2 with 2 valence electrons, it had to be beryllium. Okay, let's do another one like that real quick, and then we'll be done. I don't even know why I'm erasing this. All right, let's just go down. Let's go ahead and just skip a boot here. And let's say it's in period let's say it's in period 3, and the ionization energies are, let's go 150, 375, 621, 1232, 1573. Okay, so these are our ionization energies. So we got ionization energy 1, 2, 3, 4, and 5. Again, first ionization energy, pretty low. Okay, not a huge increase. 375, that's not a huge increase either. 375 to 621, not really, but it looks like we got a big increase from 621 to 1232. Okay, so that is a big increase. So that means that the first electron was easy to knock out, the second one was easy to knock out, the third one was easy to knock out, but then the fourth one was not easy to knock out, right? So that tells me that we had 3 valence electrons. Okay, first one, real easy to knock out. Second one, real easy to knock out. Third one, real easy to knock out. And then we have a fill outer shell, so now it takes a lot of energy. So we got period 3, 3 valence electrons. Let's go up to the top. Period 3 is 1, 2, 3. 3 valence electrons is 1, 2, 3. It had to have been aluminum. Okay, so I believe that first one was beryllium, and the last one was aluminum. Okay, guys, that is ionization energy trend. That is the hardest that we'll get as well. Okay, make sure you answer the questions and take a look at the practice, and have yourself a good day.